That's good for Arkansas. So what?
It's just all that.
My guess is there's definitely technological wise.
Hey, Meredith?
Mhm.
Do you mind if I
It's also.
phone up by
So like I
so
have,
you can feed directly in my head?
That's fine.
I'm the one trying to do that.
That was recently, I guess you could.
Can you, is that okay just right there? Even if I go over here or talk? All right. Okay.
Basically, they had a huge fentanyl bust up there. And fentanyl bust. Oh. And he was, caught up in it, so to speak. But, I think he was like strictly like using it basically. The first time he did it, his hands got like this, and then he passed out. And I woke up like 4 hours later with all of his extremities numb. And then over time, this hand came back, but this hand can only put to about here.
Okay, guys, I'm going to go ahead and start.
You can't like normal hand.
Welcome to our new star pupil in the back. Welcome back. Okay, guys, so we are getting close to the end of the semester, and I want to just go over the timing of the end of the semester. So this week we're basically having the last 2 lectures. The lecture today on software development lifecycle methodologies and data lifecycle. And then the lecture on Thursdays is about knowledge curation and retrieval from digital libraries in biomedicine. Then, so that's this week, this Tuesday and Thursday. I moved the review up. I'm going to be in China at the end of the semester, and so I moved the review up to occur on December 5th next week. So next week, December 5th, come ready with questions. I'm not going to present anything. It's going to be much more beneficial if you guys come with questions. You can retake the quizzes or go through your old quizzes or whatever. Come with questions about that stuff, and we can go through them. I will be putting a practice exam up before I leave. I'm leaving Friday the 8th, right after the poster session. So I will put a practice exam up. The practice exam is going to mirror the final. So when you take the practice exam, if you miss questions in the practice exam and you don't understand why, that's a problem. You need to go take the time and figure it out, because there will be a question on similar content and at the same cognitive level on the final. So if you have trouble on the practice exam, that's your last opportunity to go back and increase your knowledge. And so the poster session, don't forget, on December 8th, I'll be going around and I will grade posters at the poster session, and then post them in Blackboard, probably on the plane out of the country. And then on December 14th is the final exam. Tremaine will be in the classroom, so if you do want to come take the exam in the classroom setting, you're more than welcome to do that. Tremaine will do it during this class time, and then he also has it set up, since it's a final, we do proctor it, so there's like a camera on your laptop, like Big Brother proctoring out of Blackboard, and so Tremaine is going to set that up so that you guys, if you're already home for the holidays or somewhere else, you can take it remote, and that's fine as well. So you don't have to be here for the final. You can be here for the final.
What is the Blackboard proctor?
It's called ProctorU, and what it does, it uses your webcam. So there's a way you check it out and make sure it's okay. It uses your webcam, and when you're taking the test, it looks for odd stuff, like somebody standing beside you telling you answers, or weird stuff. And then and there's I think the one that we use for another setting, there's a remote company that monitors the films and flags anything funky, and then we'll flag it up for Tremaine or me to look at. And so just beware, it is proctored. You can either take it like that, or you can come into the classroom, either way. So if you take it during the classroom, same time as this, from starting at 3:30. If you take it online, it'll open at 12 a.m. on the 14th, and it'll close at 11:59. I'll set the time depending on the number of questions. I do have one person who needs more time, and I'll email and work out the time for that. But it'll be something on the order of magnitude like 5 minutes per question, or it's not like a speed kind of test. You should have plenty of time. The minimum will be 30, the maximum would be 50. So somewhere between 30 and 50 questions. I haven't written the exam yet. I'm not trying to be obscure about it. I just haven't written it yet. No, it can be open note.
Oh, okay, cool.
Oh, okay.
That's okay.
So like if we have copies of the slides and.
Open note, open book, yep.
All right, cool.
That makes sense.
Yeah, I asked a lot of my
And everyone must collectively take a sigh of relief. And we're good.
Yeah, it should not be. It really shouldn't be bad. The cognitive level will be the same as the stuff on the quiz. If the only people that I would caution and say you guys better worry is if you've gone through and on the quizzes each week, if you've gone through on the quizzes and just taken it to see what the answers are, and then gone what you'd missed and then gone back and do a new one based on that, you're more likely to have trouble on this final than you would have if you'd have said, well, I'm going to pretend that quiz is a real test, and I'm going to sit down and study as best I can, and then I'm going to go take the quiz. Because you will have gotten more knowledge retained in your longer term memory doing it that way than approaching it the other way. That doesn't mean you're going to fail if you approached it the other way. It just means you have a lot more knowledge to cram in that head. Do please bring a calculator for Bayes problems, sensitivity and specificity, stuff like that, or have one available to you.
Okay.
Yep. The only thing that you can't use is other people on the test.
Okay, so like if we wanted to keep our notes electronic, because I keep everything, I don't want to kill the free. So
Yeah. You can use your notes, you can use Google, you can't use your friends. And everybody's on the honor system. If you happen to take it before everybody else, do not talk about the questions. I will find you and strangle you.
Why are you looking at me when you say that?
No, I'm not looking at you, not for any reason. So yeah, so just, but it is not meant to be bad. I'm not planning on making it bad. Just study and do the best you can. Use the practice test. The practice test, especially if you have text anxiety, the practice test is the best way to gauge how you're going to do on the final. Okay, so so that is, guys, I went through the syllabus dates for the end of the semester. So if you just look at the beginning of the recording, that'll lay out what lectures we're doing when and the exam review and stuff like that on there. Okay, so back to the class. So today we're going to talk about software development lifecycle, which is basically how we develop software applications and the data lifecycle that accompanies software applications. And so I'm sure most of you have seen this cartoon. The processes that we're going to talk about today, their whole goal is preventing this crap from happening. So the goal of the software development lifecycle is to have predictive software development for software that works when you deliver it, and to be able to deliver the software on time. IT community has traditionally gotten a bad rap over this. It's not because they're idiots, it's because this is really hard to do. There's so many loose ends. It's a very complex process. There are often way too few constraints on the process, which makes it a very difficult activity to do, and to do predictably at high quality and do well. So I'll leave you the cartoon to ponder. So for today's talk, we're going to talk about the need for software development lifecycle, which we just did. Describe the steps in software development lifecycle. There's not one set of steps. It's kind of a general method that people follow. I've got 2 examples to show you. You should be able to compare and contrast different software development lifecycle models that people use. These are, for those of you who are going to study for the physician boards, these are on the boards for the clinical informatics specialty. We're going to talk about how software development lifecycle applies to other software. So like, it's not just stuff that you develop from the ground up. It's software that you buy, it's open source software, it's little bitty scripts that you write, it's little procedures that you write, or interfaces and all that kind of stuff. We're going to talk about different testing methods for software, then we're going to switch over and talk about the data lifecycle. And some of you are probably thinking, Marilyn, why are you putting software and data in the same slide? They really, really do go together. Although they are very different life cycles, they're managed very differently. They take different skills to manage. Unfortunately, they interact, and one can affect the other adversely and vice versa. So I prefer talking about them together. And then we will talk about a regulation called Title 21 Code of Federal Regulations, Part 11. That is an FDA regulation for data that are submitted to the Food and Drug Administration for regulatory decision making. And this regulation has had tremendous impact on software development lifecycle processes used in the therapeutic development industry and in others who submit data to the FDA for regulatory decision making. Did you have a question, Sally? Was it okay? Okay. So the need for software development lifecycle. So developing software is a really complex process. I mean, you basically start. It's like painting a picture. You start with a blank slate, and in order to come out with anything predictable or reasonable at the end, you have to have a pretty good idea of what you want at the beginning. And that's a pretty big ask in some situations, because you're often, as a software developer, you're often asking people who don't understand computer programming, don't understand software development, exactly what they want the software to do. And they have no idea what's an appropriate split between tasks for a human to do and tasks for a computer to do. And that negotiating that split, there'll be a lot of time spent in the human-computer interaction class on that. It delves into operations engineering and cognitive science, but those are really decisions for someone with an operations engineering or operations research background to make with folks about what's appropriate for the computer to do versus what's appropriate for the human to do. Often when people embark on software development, there's no concept of even making a deliberate decision about the differences between those two, which is highly unfortunate. So the capability maturity model that we talked about in the last lecture, that actually was an attempt by the federal government to have predictive software development, because the federal government had so much trouble contracting out software development to folks that they worked with Software Engineering Institute to create that capability maturity model so that the federal government could look at an organization prior to award of a big contract and gauge their readiness and their likelihood of success at a large software build. So the capability maturity model that we talked about last time really came out of the vast need for software development lifecycle. But the capability maturity model is not enough in itself, and it is not a software development lifecycle model. And so that's what we're going to talk about today. So when you develop a piece of software, this is kind of a general SDLC, or software development lifecycle approach. So first there's kind of some planning about what you might want the software to do, what you need it to do. And then you get a little more deliberate about defining those specifications. First, writing conceptual level specifications or functional specifications, and then getting more detail into the computer design, the more technical design of the software. And writing technical specifications. So there's often in software development lifecycle that the define and design step. Sort of define is more conceptual level that a user can write, and the design is something that would be a transition off from a user or an analyst to a software engineer. The reason is that, just as we've seen with different knowledge representations, where different representations are better at storing different kinds of knowledge or enabling different things, the different programming languages are better and more efficient at some things versus others. And so when you have a programming language that might or might not do some things well, and a data storage mechanism, maybe it's a graph database or a document database or hierarchical or network or relational or whatever, that database has certain capabilities too, and it's going to excel at some things and be crappy at others, like we saw in Mike Lightsey's presentation about the CAP theorem. And so you've got software that has different, programming languages, different capabilities, data storage, different capabilities, different environments, different capabilities. And so really the goal of the more technical design is to optimize the programming language and what needs to be accomplished in the data storage together. So it is, a user can't do the technical specifications, whereas a user could and should do the functional specifications. The next step is the building, and that's what you think, as somebody sitting at their computer writing code. And building is different depending on what type of software it is. So if you think about an app that runs on your phone, most of those are pretty small and have very limited functionality that they do. If you think about the functionality in Epic, oh my, you can do hundreds of thousands of different things in Epic. Make this display, make that display, chart this information, chart that information, send an alert here, get an alert from there, all sorts of different stuff. Whereas in many simpler applications, you might only have 2 or 3 main functions that you could do. For those of you that are employed here, we all do an open enrollment. What we had to do, we had to log on the website and we had to go and say if we were going to use flexible or dependent care spending account. Really simple software development. It had to be up on a website, and it had to be able to find our record, let us log in, authenticate us, find our record, and indicate what our choices were, and then save them, and that's it. Think about that compared to Epic, where Epic does that hundreds of thousands of different ways for different pieces of data and in different workflows. And so the building phase is different if you're building a big, huge application versus a little bitty teeny app, or versus just a script. When we went through and wrote some SQL code with Sharab and Manez, we were just writing a little SQL script. That's not even a software. That's just a data retrieval statement or setting up a table in a database. Very, very simple scripting. Some software development lifecycle will apply to those, and there are places where you might want to apply some of those concepts. But just remember that the building is vastly different depending on whether it's a big project or a small project. And then there's some testing that occurs. Testing has been a real sore spot traditionally. I remember back in my doctoral career, after I defended my master's, a guy went behind me and defended a master's or a dissertation, and he had built a big computational model for something, heat transfer through nuclear fuel pins or something. And one of the professors says, well, how do you know the code works? Oh, I know it works. Well, did you test it? Oh, no, I know it works. What edge conditions did you test? Oh, well, no, I ran it on the data, and I know it works. Okay, that is the wrong answer. That is not testing. So we're going to talk about some formal methods for testing. Testing is something that a lot of people don't want to do. They don't like to think about, but it's critically important. It is always a separate step in the software development lifecycle. And then there's deployment of the software. So you can have a piece of software that comes through development and testing just beautifully, and then you go to implement it in the user environment, and terrible things happen. And thus, there's this deployment step, and in informatics, there's a following evaluation step, not just deployment, because the terrible things that can happen in healthcare are bad comparatively to something that might be a simple app for a grocery list on the phone. So we, in healthcare and informatics, add in the evaluation step of it. And then we're back to planning again, and it's a circle because once you build a piece of software and put it out there and start using it, it's going to have changes. And so it goes around and around and around. Yeah.
Related to the Tower achievement, I think it's similar to
Yeah, it is. We generally don't think of the Tower of Achievement as SDLC, but you're right, Hoda, in that the steps are very similar. But the difference is that this is geared towards software development, And the Tower of Achievement might or might not be software. It could be a process or a chart or a new tool, a new information intervention. So the Tower of Achievement doesn't necessarily have to be software. There are a lot of people that equate informatics with computers. I think informatics actually in its heart has nothing to do with computers. Informatics has to do with the underlying information and knowledge and how that's represented and used. We use computers as a tool to get some of our information interventions out there, but there are definitely people that would disagree with that. And so after I've told you about all these nice steps in the software development lifecycle, they are often blurred. This is a different rendition of it, different rendition of the steps. But what I'm trying to communicate is that these are not distinct steps, and it often doesn't go cleanly through them. And yeah?
So I'm excited this. Is deployment different than actual implementation?
No.
If you do the same thing?
Yeah.
Okay.
It's just that different disciplines think about it differently. So like deployment of an app on the App Store is one thing. Putting a new version of Epic in the clinical environment is different. So it can mean different things to different disciplines. So a lot of the steps kind of blur together, and that's what the next 10 or 15 slides or so are going to talk about different methods that people use to navigate those steps in the software development lifecycle and different arrangements of those steps and why they do them. And the reason why we even care about this as informaticists is that when we design some information intervention, we need to very clearly understand and be able to interact with a software developer if it's going to be implemented in software, so that we understand how they're going to develop it, and we can help make decisions that arise in the development process and be there when requirements need to be clarified, be there to help write tests for the software and things like that. So as an informaticist, I care very deeply about the model that's used. There's, one of my projects that we're working on now, we're using an agile methodology. No way in hell I'd do that with a different methodology. But there are other projects, there's no way in hell I'd try agile on. So it depends on the project. And as the person who has a big stake in what's developed, I really care deeply about how it's developed in the process that's used. So the first model, this is the oldest model of software development. It's called the waterfall model. And the reason is that it just kind of goes one step, then the next, then the next, then the next, then the next. Now in practice, okay, this never happens like this, and it never happens cleanly, which is the root of the problem with this model. So, this would say that basically you just, around that circle, you just step around that circle one after the other and go from project planning to defining requirements to design, then development, then integration and testing, and then installation, and ultimately acceptance of some type of the software. And so the characteristics of the waterfall model are really this step-by-step progression through the software development process. Oops. The next is that the waterfall model, when we talk about the regulations at the end, we're going to talk about documentation for software that needs to comply with 21 CFR Part 11 or other federal regulations. This whole process has to be very, very well documented. And because the waterfall model sort of progresses sequentially, it's very easy to do that. If the requirements change in the waterfall model, you have to go all the way back to the beginning, which is a major problem with the model. It's why it takes longer. It's why people have trouble with it. Because if you get all the way down to testing and you find a problem, then you got to go back up and fix the requirements definition usually. Sometimes it might have to do with planning. We had an installation get done on the wrong server a few weeks ago, and we had to go all the way back up to the beginning of the process. We weren't using this model, but things happen unexpectedly. Not just wrong server, but the whole wrong environment. It was installed in the Windows environment instead of on Linux. Big problem for us. So in Waterfall, if you get down and then if you get the user acceptance and the users say, oh, no, I needed it to do this, not like that, then you go all the way back up to the beginning, which gives software development a very bad rap, and for a lot of ways, undeservedly bad rap. So since it's executed in sequential order, kind of parallel work is not possible. There are many cases in software development where there's different pieces of the software, and you really want to have different people working on those at different times. And you want to get those as fully developed as you can and tested. And it's much harder to do that kind of parallel work in a waterfall model than it is in some of the other models. So because of that, it's perceived as slow, it's perceived as inflexible because of that sequential nature and because of the rework problem. If you get down to the bottom and have a problem, you got to go all the way back. There are, though, some cases to use waterfall. When I have a little tiny project, I would never try to do some iterative methodology with it. If it's very small, waterfall works great. And I'm going to march right through those little steps. And if I have a problem, it's not a problem. The project is small. I go all the way back to the beginning and redo the steps. So, for example, we had a piece of software because it was installed on the wrong server and we needed it in production for a project that actually wasn't going to be done under the regulations. We had people go ahead and run the suite of tests in the old environment just to bang on the software and see if they could catch anything big. So when we get in the regulated environment, guess what? We have to re-execute those tests all over again. But executing them in the old environment was enough to give the non-regulated project some assurance that the software was working okay and was able to kind of keep them on timeline doing that. So for small stuff, this is not a big, it's only 150 tests. It wasn't that big of a deal. Other things, if requirements are not likely to change and requirements are clear, waterfall works better. It has a much higher likelihood of success under those circumstances because you're less likely to have things that propel you back to the beginning of the process. Is this making sense so far? You guys go with this? Okay. All right. So what people started to do is they started getting creative with these software development processes. And so they took waterfall and they said, well, you know what? I'm going to develop a protocol before I march all the way through and get to the end with a major, $2 million piece of software that the customer doesn't like. So they put in this prototyping step. So that was one sort of early attempt at mitigating the risk of a deliverable that's not accepted with the waterfall model. There's still risk, though, because it's kind of hard to draw the line, and some people would spend much too much time developing the prototype, and then the prototype starts looking a little bit more like actual real software because they've put several months into it, which tends to delay the project. The other issue is large changes. Sorry, that's supposed to be a P there. Is having large changes after the prototype. So, when the prototype does its job and ferrets out problems that you have, you may actually have a big change. And so you've mitigated some of the risk, but not all of the risk with the waterfall model. So that's when people say a prototype model, that's often what they mean. Another model is called the spiral model of software development, and this you basically so it starts here where that black line first is on the axis and it goes around this way, so counterclockwise. And so you basically break up the software development into modules A and B and C, or however many modules, and you start developing those modules. And so it's basically you're starting with some core functionality, and then you're building on that functionality through successive turns of the crank of the spiral model and adding more functionality up on the project. And so, for example, if you start at the beginning there where the black line starts, you make requirements for Module A, then you design Module A, code Module A, test Module A, and the user could start using it. So you define Module A as some piece of useful functionality. If I was going to build an EHR system from scratch, I might start with registration. Module A might be patient registration. And I would go through my little steps for Module A and deliver Module A to the client and say, okay, start registering your patients and let me know what happens. And so then in Module B, I might add on medical coding and billing. And I might also say, all right, y'all dudes that have been using this in production now, registering patients for the last 6 months, tell me anything that's problematic about registering patients and I'll fix that too while I'm doing Module B. So you just sort of expand the core of the software into a more highly functional process. Most of the EHRs on the market were developed in a similar way to this, where they've sort of been built upon.
I worked for a software company that was CRM software that designed this kind of mentality. There was additional modules that were continually being developed to add new functionality to the system. And would have everyone go through and be using it and testing it, finding things and finding, oh, it would be cool if we had this and that developed into the module.
Yeah.
So on and so forth, and the software just keeps getting bigger. And then eventually they revisit the initial Module A they designed, and now that they have all this new technology implemented in the additional modules, they then update Module A to reflect everything else.
Yeah, that a lot of the vended software, the older vended software, was developed in this model, and it works, right? Because it's just what Robert said. You're out there in production, you collect some changes, and then you have some improvements you want to do as a company. You bundle them up all together, and those are your next release. And you crank the turn of the spiral one more time.
And then you can also sell the individual modules rather than the software.
Yep. So that's sort of the spiral model. It works great for longer term projects. If it's short term, it's kind of hard to have 2-day or 3-day little iteration things. It does work when the requirements aren't clear. If you can get some requirements for something that you can build and get out there, a customer's interaction with software will generate additional requirements. That's like the one thing that is certain. It works pretty good for brand new software or first release because it gives you some experience with it internally before it's in full use in prime time. If you can chunk the project up into modules, some projects I'm sure probably can't be chunked up into modules. So for those, this doesn't work as well. If you can't get some core bit of deliverable functionality to do. If the project is medium or high risk, this does mitigate some of the risk of the waterfall model because it gets stuff in use earlier. And then if you have to have an early deliverable, if the sponsor's like, just give me something now, immediately, then this isn't so bad. It does get something out into folks' hands pretty quickly. And so some characteristics of the spiral, it is a little more flexible than waterfall and more tolerant to changes. It deliveries by chunk or module, it does. When they do changes in when you get requests or changes that come in and you're managing it in a spiral model, you generally kind of classify those changes as minor versus major. Minor is something that you can get in the current module that you're working on now. It's not that big of a change. It's not going to kill anybody. Major is something that is too big to get in the current one and you have to put it in next year. So we had a question about some functionality on a system that we're putting into production now, about new functionality that it didn't do that we would like for it to do. So we called the vendor. The vendor says, well, here's the workaround for it if you need to approximate it, but we really can't do that today. But it is in the next release. So they're conceptualizing it with bigger changes next release in the spiral. Of course, that might come out next year, maybe. It is perceived as being a sequential model because you do run these little waterfalls in there for each turn, and it is perceived as taking longer and costly because you have to turn the full crank to a usable piece of software and go through deployment, and then you're starting your next one. So it mitigates some of the risk, not all the risk. Another software development model is called the V model because it looks like a V, or the VV model for verification and validation. The approach to mitigate risk with this one, if you start up here on this side, there are specifications and requirements, and then high-level design, lower-level design, programming, and actually, writing the actual computer code. And then as you start to go up the other side, there's the different types of testing that correspond to each of those stages in the cycle. So whereas some of the other models, they don't exclude some of these verification and review steps here. These steps are built into the V model. So for example, like for the business specification, there would be a review and sign off on those. For the system requirements and specifications, there would be a walkthrough for those, where people get in the room and have a walkthrough or other reviews. So there's more formal reviews of the actual specifications and design reviews in the V model than there are in the other models. That doesn't mean that you can't do waterfall with these reviews. You certainly can, and some people do, and that's how we get all these different variations of software development lifecycle approaches. Does that make sense? Okay.
So are each of these done in tandem? I'm looking at the flow chart.
Uh-huh.
Are each of these done in tandem, so you do ERS
No.
and then acceptance, or
No. And they're...
start on the left, get down, and then start translating over? Or
Yep. So for example, when you write the business specifications, you will write the tests for user acceptance testing, but you can't execute them because you don't have the software yet. So the arrows sort of just link up the test with the specification or the development activity. But in order, you can develop those tests when you develop the specs, but you can't execute them till it's done. So like when we're going back to our rules-based stuff, we use, in clinical trials, we use rules to clean data a lot, that, in multi-center clinical studies. And so when we would write them, we'd write the specifications for the rules, and then the same person that wrote the specs would also write all the test data. And would hand the programmer the specs and hand the tester the test data. So that the person that, because if you're testing them according to how the person thinks the rules should work, you catch errors in interpretation in the code a lot better. So that's sort of an example of you write the spec and the test at the same time. Make sense? And then for some folks who do computerized testing, they test their code with other code. They'll write the specs or get the specs, and then they'll write the test first, and then they'll start developing the code. So either way. And so when to use the V model. So if it's a small project, or kind of up to a medium size, but you probably wouldn't want to do it on a big project because it's just so sequential. If the requirements are clear and stable, the V model is great. If the project is complex, the process of writing those tests as you're writing the specifications can often help to clarify the specifications. So that's another place when, if it's really complex, that can help with getting some of those specs clarified. Characteristics of the model. So it is sequential. A big characteristic is that V shape, where tests correspond to each of the different types of specifications or other development activities. The testing in itself is a risk mitigation adaptation, as is the review, verification, review of each of the levels of specifications and design. It is fairly easy to document because it's sequential, and but it's pretty inflexible to changes. Because if you change specification because you wrote the test when you wrote the specification, you also got to go back and change the test that you wrote. So that makes, it fixes problems here. It's like whack-a-mole, and other problems come up over here with it. It is perceived as more costly because you're not just managing a set of specifications documents as you go into the software development, you're also managing the tests that you're writing for all of those steps in there. Uh-huh.
So the difference between this method and waterfall model is just that I do the tests.
Mhm. Yeah, it's just that.
Sequential, it's still sequential, and still I have to go from ups to down.
Yep, exactly. Now, that doesn't mean you can't say, I use waterfall and I also do these review steps. You could do that, and that would be fine. Nobody would, these aren't, it's not like a train track where you have to stay on the track. If you're running a waterfall model and you want to mitigate your risk by writing tests early or by adding in design reviews, you are more than welcome to do that. And that doesn't mean you're not doing waterfall because you do that. So think of these as think of them as cookie cutters. When you're making cookies, you stamp them out, but then you might change them a little bit after you stamp them out. So there are tons of variations on these themes that people actually use in practice. The next is that I'm going to go to, and this is the last of the software development models that I'm going to talk about, are iterative models. There are iterative models, there are agile, there's different processes that people use. They call them iterative modules or software development. And so this is an example. You might have and I just got this example off the web. You would have a kickoff meeting, and you would come up with a little bitty thing that you could deliver immediately. So it's kind of sounding spiral. The difference in this in spiral is that in an iterative model like this, you're not necessarily building on prior stuff. You could be. There's nothing that stops you from doing that. But you're also developing completely parallel pieces of software. So on one of the projects, we have somebody writing code to extract data out of the database. We have another person writing code to write the discrepancy report that they're programming based on it. We have another person developing data entry screens on the project for other data. And we have another person working on code for statistical analysis. So we tell all the people, here's the common data model. This is what the data is structured. All y'all different people start writing your code. And they decide, we have a 2-week, we call them sprints or iterations. They decide what's going to get done in that 2 weeks. And they manage it. They have a 15-minute stand-up meeting every morning. What did you do yesterday? What problems did you have? What are you going to do today? Do you need any help today? And so like the whole team is like just pouncing on it every day on these little bitty deliverables. Kat, are you with the team on this on PCORI? Are you in? Okay.
The reason why we are going to be done with ICD-10 codes next week.
Yeah.
Other than other autoimmune concealing gear, we decided that we're going to include things that might cause autoimmune-like symptoms. That's okay.
Yeah, no.
That's okay.
But it works though.
I mean, like seriously, before I was completely lost, like in terms of managing it, and now I'm not going out for it.
Yeah, it's a refreshing way of working. It's an ultra accountable way of working, but it's refreshing.
If you're kind of unfamiliar with the task, you're not really quite sure how to plan it, like what your bandwidth is,
Yeah.
in terms of what you need to put into it. I started out with having down those ICD-10 codes, like a list of 34, and I started out with doing like 2 to 3 a sprint, and now I'm up to 10 a sprint with 5 per stretch. That's how we're gonna get it. I think I knocked out like 24 in the last 3 weeks.
Yeah. So the cool thing about these iterative methods, we use Agile. We have a Scrum Master. The Scrum Master is the person that runs the stand-up meeting every morning. And some people are just excellent good at doing that. And so literally for iterative, you can put anything into the sprints. We put requirements development into the sprints. We put getting data into the sprints, analyzing data into the sprints, software development into the sprints. Lots of stuff that needs to be done we put into the sprints. So when to use them? If the project is large, like this thing is heinous. It's not like an 8-armed octopus. It's like a jellyfish with 1,000 tentacles. And this helps us manage it. It helps us manage the work streams. When only some of the requirements are defined and others can evolve or be discovered is another place where you might want to use more of an agile methodology. Because one, jumping in on something that's low risk and a little bitty bit of work will help uncover requirements for the next iteration or for the next thing that needs to be done in a safe way, so that if you end up totally screwing up and totally have to scrap work, you're scrapping 2 weeks worth of work instead of 4 months. You can also use it, though, when the requirements are complete and clear. It's a lot cleaner and less messy when the requirements are clean and clear. When the requirements are not clear, you end up having people say, wait, we haven't defined what goes on the discrepancy report really well. We need to put finishing those requirements into the next iteration. So you get kind of iterations that are focusing on requirements and development sort of different pieces. There are some characteristics of it. So it is very tolerant of requirements changes, because there's just these little bitty modules that you affect. There's this built-in clarification of requirements, because after you do an iteration, you have something that works, some final product, and you can show it to somebody and say, is this what you meant? Is this what you wanted? There's testing of each iteration. As they're developing code, they're actually testing, so you don't get down way to the end and figure out, oh geez, some fundamental underlying assumption I made was critically wrong 2 years ago when I started designing it. It completely prevents that. It works really well. You can have parallel work, and the cross-functional teams are involved earlier, so testing's ongoing. The minute you get something that reasonably looks like it's going to work, you can start the testing process. It is perceived as easier to measure progress and to manage, and because of that, it's perceived as being less risky. There's probably some literature out there evaluating it. I don't have my head in that literature, so I have no idea. But I can tell you, I often get responses like I just got from Kat about she going from more of a waterfall approach to a more iterative approach.
Well, even like with the type of the project that we're working on, so the conductive and parallel development, like what I do is very encouraged what you can do.
Mm-hmm.
So we were like, almost like take that we were two sides of the same coin, but I have to do my work with her to do her work, and it comes back full circle with me and Miriam doing the testing and validation. So, and you're right with measuring progress. I think
It's huge.
Yeah, I mean, like a month ago when we started this, I couldn't tell you where I was, but now I can give you exact numbers and how much I've been able to grow my list.
Yeah, it's huge. It's often folks in IT will really be perceived as, well, they're not managing their work, or they can't manage their work, or they don't know how to manage their work, or they're hiding their work from me, so I don't know that they've done nothing. But that is like really not the case. It's just that this is so complex and so difficult. It is, unless you have really expert management of it, it gets behind, and it's difficult to track, and people they don't really have the ability to report out on progress. It's like if you think it's like if you say, Meredith, for the new software you're developing for me, when is it going to be done? I'm going to say, well, I only have about half the requirements. Given the requirements that I have, I think it'll probably take me about 10 months to build and probably about 30,000 lines of code. And then the requirements flex, and then it's 20,000 lines of code. Whoop, nope, wait, new requirement, 40,000 lines of code. So as software development has this ability to shrink and contract, which makes it very difficult to predict. Whereas if you're using on an iterative model, at least you can say, this is what I'm doing in the next 4 iterations, this is how far down the road I think it's going to get me to the goal, and this is when I'm going to be done. And you can report regular progress on it much easier.
Having a good leader to tell the client that no, that's not what you want, you're going too far, and you're going to exponentially increase your costs, and it's not going to really do what you want it to do. If you add in all these features, you're going to crowd it out. That's also a big part of it.
Yeah, that's
no
huge.
One no.
Yeah, for us, her name's Anita.
Yeah.
Yeah. It's huge. You're right, because if you have somebody clueless interfacing with the user or the sponsor or the customer or whatever, they can say, oh, that sounds like a great function. You should definitely have that in there. That sounds wonderful. And then they turn around and ask the developer, and they're like, oh, yeah, man, it's going to take 6 months to put that in there. We're not architected to do that.
Well, and even then, for it's a simple example, for the company I work for, we have an activity tracking option to like log activity types. So managers can see what exactly employees are doing. And, I'll be on the phone with managers, documents, I still do some contract work for them. And no one put in 30 different activity types. I said, no, you cut that list down to 8. 8 max, because otherwise, your people are going to be losing all that time trying to figure out what I do from where. And,
Yep,
crazy things.
It really takes very solid management. So the last kind of thing I want to emphasize about the different models is that, like, Agile is not in opposition to a waterfall model. Because when you do the little iterations in Agile, guess what? Those are little bitty waterfalls. They're just little. Now, it makes the documentation crazy, because instead of saying, here's our design specs, here's our unit testing, here's our functional testing, here's our system and integrated testing, you're like, here's the stuff for iteration 1 to iteration 2, and all the way up to iteration 203, and the testing for one function or another would be somewhere within that amount of documentation. So the documentation is a lot messier with Agile. For that reason, a lot of folks in regulated industries have been very scared of doing it, because they have regulatory departments that are holding them to a soft, waterfall model, because the documentation, it's very clear how the documentation meets the intent of the regulations. In Agile, it's a little more risky. And with all those iterations quickly moving and you're doing documentation at the same time, it's much easier to have stuff that's less rigorous in the documentation. So you just have to be very careful about it. So, but they're not in opposition. So if I were going to ask you questions about these models, since we're getting towards the end of the class, I'm going to ask you questions like, which of the following is a potential way to mitigate risk of requirements changes with the waterfall model? And I might have one of the options for the responses would be, maybe prototyping would be a potential to mitigate those risks. Maybe adding in some document reviews earlier on or something like that. So it's going to be, because the driver in these new models, not all of them are new, but in creating new models throughout history it's all about risk mitigation. And so really if I've got a risk of requirements changing, or I have a risk of cost overruns, or I have a risk of timeline overruns, or I have a regulatory risk that my documentation's not as clean as it needs to be, what can I do to mitigate? What can I do to change the process of software development so that I can mitigate those risks? Make sense?
So Agile is the iterative, correct?
Yep. Yeah, Agile is a very specific methodology. It is one of multiple iterative methods. I just kind of use it as an example because a lot of people run it today. And who knows, there's another model that people make fun of called Big Bang. That's basically like you just put some developers in where there's no requirements and some users, and you expect software to come out the other end. I'm not really sure anybody ever actually uses that, but so the next kind of thing I want to sort of transition into talking about is that, like, not everything is a software build. For example, one of the systems we're just putting into production now, it's an open source piece of software. We didn't build it. We didn't change the source code on it, but we were required to test it and validate that it works appropriately in our environment and for the functions for which we're going to use it. So the SDLC applies because the testing of the SDLC methodology applies to us, and the regulatory authority cares that we have looked at the vendor's software development. Easy for us because it's open source. The vendor, there is actually a vendor of it, even though it is open source, so we can go there and audit them and check them. For true open source stuff with an open source community, it's a lot harder. right? How are you gonna audit that? Where are you gonna find the requirements and the specifications for open source? And how are you gonna be sure in your testing that somebody didn't leave a back door in the open source software so that some of you, yeah, I mean, regulators hate that stuff. And information system security officers at organizations hate that stuff. There are many organizations that will not use open source code because it is very hard to know if somebody has put malware in the base computer code to the application that might enable them to tunnel into the system later once somebody has it in production. And it could create a big security risk for an organization. So there are a lot of organizations that just won't use open source software because of that. There are other types of things like the code written for use within an existing system. So for example, in Epic, the decision support rules called best practice advisories, that's code that's written within Epic. You don't change the code for Epic when you write those. You put in a little script and it says, if this happens, if you see this in the data, then do this. Make this little alert. So SDLC applies to those as well because you have some requirements for them. You need to make sure they're correct. You're going to have some testing for them. If you're doing it in a regulated environment, you're going to have to document that you've got some requirements and that you did some development and that you tested it. So much smaller, lighter version of SDLC in the corresponding documentation, but it still holds for even very small pieces of code, which includes like rules within systems, code that you might write to write reports out of systems. That code needs to be validated as well, depending on certain circumstances. Like if you're going to use it for decision making, you at least need to make sure the report's right. In a regulated environment, you need to prove that you have tested it and prove that the report is right. And then there's also custom developed interfaces between systems. A lot of times you'll move data from one system to another. Like with e-prescribing, data goes from your provider to the pharmacy. With a lab, your lab sample goes and data comes back from the lab to your provider's EHR. So any of those interfaces that have to be developed, some are marketed, you can buy them, interfacing system X to system Y and plug it up and it works. Others of them, those interfaces have to be developed. So that is software development and requires some of the same methodologies. And so I wanted to say a few words about testing. There are lots of different kinds of testing, and some people use the same words for different things, and the definitions aren't very clear. So I'm going to just kind of try to give you an overview of general different types of testing methods. And it'll sort of follow the V model, because there's sort of different types of testing at those different levels. And so unit testing is sort of the lowest level of testing. Unit testing is something that a programmer would do after he or she writes some code. So they're going to write it, and then because they don't want to hand it off to somebody and let it have an error, they're going to do what they can themselves to test it. In a regulated environment, even that has to be specified in procedures and documented. In other non-regulated environments, that doesn't have to be documented. It's an expectation that when the programmer writes the code, the programmer is going to, number one, document it well, and then they're going to test it well. And so really it occurs during and right after programming, and it occurs before the software moves to the next step in the process. People also refer to this as white box testing, glass box or open box testing. If you think of a black box, it means that like it's a box and it's inside and you can't see what's in it. You have no idea how it works. So when they say white box testing, they mean that you know what's in there. So in other words, in the example I gave earlier where we had data cleaning rules, and I would write the specs for the rule, and I would write the test data because I knew exactly how that rule was going to work and be programmed, and so I would provide white box data. Because if there are 4 or 5 logic conditions in one rule, then to test it, I'm going to march down with test data at each of those logic conditions and write conditions on either side of ranges so that I know the range is in the right place. and I'm going to write for each logic condition test data that tests each branch in the flow control. Does that make sense? So like if you think of flow control in a logic algorithm, like a flow chart, so it might say if a patient is female and a patient's had an acute coronary syndrome diagnosis and they're being discharged and they don't have a contraindication, give them aspirin. Make sure they're discharged on aspirin and a beta blocker. So the logic that says are they female or not, I would need to test that. I would need to test the logic that says acute coronary syndromes. I'd want to know what codes were in that. I want to test codes that should be there to make sure they're there, codes that shouldn't be there to make sure they're not there. I'm going to review the code, make sure they're all listed in there, no typos and stuff like that. Then the next one was if they don't have a contraindication for it. There's contraindications of aspirin for like GI bleeds or something like that. Maybe other meds that they're on. If they're already on a blood thinner, maybe you don't want to do it. And so you need to test that logic around those contraindications to make sure that your code's picking them up correctly. And then you need to test the logic conditions around whether or not they're being discharged. Like when in time. So like is it the planned discharge today? Is it the nurse has already met with them to discharge them? Where exact? What do we mean by discharge and where in the process? And what logic am I using to determine that it's a discharge? So you would put in test data. So in order to test just that algorithm, I might have 30 different test cases of test data that I would type in patient 1 through 30 that have all these variations of what would make that fire and not fire correctly and incorrectly, and test that code in that way.
So we change the variable and see if the code is going on right or wrong.
Yes, exactly, and that is test data. And so it's often impossible to write a complete set of cases for it. And so you want to pick test data as close as you can. So for example, if I want to test that a best practice alert is going to fire if blood glucose is less than 60. Or less than 40. So then I'm gonna write one test case that shows it being 39, and I'm gonna write one test case that shows it being 40, and I'm gonna write one test case that shows it being 41. So I've picked that data specifically around how the logic in the code operates, and so that will be white box testing. Because I know how the code operates and I'm going to do that. Typically, it's the programmer doing that or the person that did the technical design that's going to write the white box tests. But often it's tons of test cases. When we validated, the last big system I validated for FDA compliance for Part 11, we had paper documentation, we had it all in binders. If we lined them up from here to here, it would have gone from all the way over there to all the way over there. Tests and test output, test data, tests and test output. And so when an auditor came, we would give an auditor the validation report that says what tests were run when in the process, and they would go down and randomly pick, I want the data for this test and this test and this test. We would go back in our little binders, find the right binder, find the right test, and show them to the auditor as objective evidence that we had tested the system in the way that we had specified and said that we were going to test it. Fortunately, Joint Commission does not do that. So that's white box testing. So then if we kind of move up a little bit, so this is sort of this unit testing, we get into component testing. That's more sort of, it tests each little module that's being developed of software. So you might have, if it's a database application or some piece of software, you might have code that gets data and brings it. And you would have that be a component, and you would test that as a component, the code that gets data and brings it. So in there, it's basically you test them as a module, a little piece of working software. The next level up is system integration testing. So after you know that each little module, and some modules aren't very little, but after you know that each module works appropriately, then you have to test how they all work together. Because like if you did Spiral, and if you really did develop it in modules, say it's my little EHR. So I might have patient registration part, I might have a patient billing module, I might have a admission discharge transfer module, I might have a lab module for HODA, I might have a cardiovascular module for Sally, I might have all sorts of 50 modules. After I'm sure all 50 modules work well, then I'm going to test how they work together and put test data in that specifically tests movement of information from one module to another, or use of data in a module from another module and how that data gets from one.
Testing the interfaces.
Mm-hmm. Yeah, so like lab is a great, so like when if you put a new analyzer online, then you would do this interface testing to make sure that it's working appropriately and not sending weird stuff. So that's the integration. So when you hear integration testing, think interfaces. And then system testing is the next level, and that's basically the whole application. It's generally done by the software development shop before it's given to somebody else. So all of these other testings are generally done by the software development shop, and I tell you that kind of depending on how an organization sets their roles and responsibilities, it might or might not work that way. But generally, the plan is in a lot of organizations that system testing and everything below it in the process, earlier in the process, would happen within the software development shop. And then they would turn it over to the users or some user representative and do user acceptance testing on it. The user acceptance testing would generally, when I write user acceptance tests, I write functional tests for them. So this software we've just installed, for all 150 different functions the software performs, we have tests written for all of them. And so when we do our user acceptance testing on it, we run all 150 tests to make sure that it works as we think it should.
System testing is done by the developers also?
Yeah, but it's after.
And the unit is before.
Yes. So if we look back, whoops, I'm sorry. If you look here at so after the code is written, then you start doing the unit testing, and then the component testing and the integration testing, and then system and acceptance. And so everything below acceptance is generally done within the software development shop. Although I will say a lot of organizations blur those lines and use different roles, have different people doing different things. So for example, I worked in one organization, the IT group had a software QA group within it. And so they did everything up through system testing. And then they turned it over to the business units, and the business units did the user acceptance testing on it. Make sense? Now, all of this is not to be confused with usability testing, which is a more cognitive engineering approach that's done in human-centered design. And if you take the human-computer interaction, how many of you guys are thinking about taking human-computer interaction next semester, by the way? 1, 2 people, 3 people. Human-computer interaction. 3. So 1, 2, 3, 4. Okay, 4. Sally's deciding. So if you take human-computer interaction, you'll spend a lot of time understanding the field of cognitive engineering and human performance and how a computer interacts with that. And so there are special testing ways for usability testing that can help you discover that you've designed a piece of software very poorly. For example, like some usability testing will track eyes. So like they'll use my webcam on my Mac, and they'll say, Meredith, do these 3 tasks in the software. And they'll put the camera on, and they'll track where my eyes go. And so they can tell if they say, do task A, and enter the prescription number in to refill your prescription, and I'm going, like all this looking around, they see that on the eye tracking data, and they say, wow, the user interface is really bad. She can't tell where to put the prescription number in. Or she can't find the function that she's looking for on the user interface. And so the human-computer interaction class will go over methodology for doing that in the design of software and using that also to evaluate existing software. But different than this testing. This is just, does the crap work? usability testing is it designed reasonably for a human, and is it designed to improve or impede human performance? Okay, so everybody take a breath. We're gonna switch. God, I had no idea these slides would take this long to go through. We're going to talk about data lifecycle. So we had the software development lifecycle for software, but data also has a life cycle to it. And they're not the same thing. The data lifecycle literally refers to only the data in the system. So remember when we were talking about relational databases, we talked about data and software independence, that the relational model started giving us that independence. So the data are stored in a relational database. The software is up here, and it uses them. It reads from, writes to that data store, but it's different, and it's protected from underlying structural changes in the data store through the logical data model. And so thus, having software and data independence means that data can live on a different life cycle than the software application. In the old days, if you had an application, your data would be in there. It would be in files that were used by the software system. Like in there, like your data would be in an Excel spreadsheet. And so if you throw the software system away, you would have to go to elaborate mechanisms to access the underlying files and write code to get your data out. So data, and sometimes they were in proprietary formats. When we migrated at Duke to Epic, some of the systems that we decommissioned and pulled out of production were systems where the data were stored in proprietary files, like the Philips OB trace views, an example of one of them. And the Hilltop binary transport for GE's ECG system, the ECG waveform system, just two that kind of come to mind. Those the data in those systems were stored in proprietary files within the system. There was no separate data store that could be accessed. We couldn't get the daggone data, and vendors are zero help, absolutely zero help. The GE is actually a binary file. It's as ridiculous as you can possibly be. But today, the expectation is that there is data and software independence. And so if we turn around today and decide, you know what, we hate Epic, or I'm throwing it away tomorrow and I'm going to Cerner, we can get our data out. So we take all of our data and we take it and we dump it into the new Cerner implementation. Now there's a lot of mapping, and there's a lot of, it's like fitting it back into a different common data model. But the data and the software today are independent, such that data that might have been collected 20 years ago in a different system can be part of a migration into a new EHR system, and that data lives on and might still be considered relevant. For example, birth certificate information, childhood immunizations. There are some pieces of data that are important over a long time frame, and thus the concept of data life cycle. Because when you rip out and replace a system, you have totally separate decisions to make about what you're doing with the data. So for example, when a lot of people went from a paper world to an electronic medical record out at primary care practices, a common practice was literally to scan the paper chart and make it available in the system as a PDF document, an image. Now you can't search it. Half the time you can't find it, and the other half the time you can't read it. However, that was the data lived on paper. That's how the data lived, and that was the migration strategy. Today it's obviously not that, if it can at all be helped, but people did that. So the data life cycles might not coincide. Like you might have data that needs to live on, but the system's done and you want a new one, or you can't stand the developer anymore and you need to change vendors. And so you need to make provisions for having the data live on and managing the data even long after the system is gone. Make sense? Okay. So for that reason, today, whenever you implement a new piece of software, data migration is always a consideration. It may be a quick consideration, as in, well, I don't have any data worth migrating in, so we're starting all over again. Or it's cheaper to start all over again. But it's a consideration, and it's an explicit decision. So the there's this thing. There's a lady, Danette McGilvray, who has published a book about information quality, and she has this model called POSMOD, or POSMAD, however you want to say it. And so down the left, it is sort of a model for the data lifecycle. It's the more cogent model out there for the data lifecycle, so it's the one I tend to think about and use. So first, there's some planning for the information resource. Then there's obtaining some data. Then there's storing and sharing the data and maintaining it. The data don't have any value to the organization, according to how the information quality people think about it, until you get down here to apply. So until you get some value out of the data, they're absolutely useless, is the way a lot of people think about it. And then there's a time where you dispose of data. You know, there are sometimes it's an unfortunate decision. Like we migrated systems and we didn't think we needed all the data, and we only got about 30% of the data. We didn't get the full record. We just got the pieces we wanted and we threw away the rest. That happens, and sometimes that's okay, sometimes that's not. And other times data have a half-life. So if like I have contact information for people, because I do record linkage, I kind of care about that, and I can use that to my advantage to identify people later. But that data has a half-life, especially in a very transient population. So it may be that contact information 10 years down the road is not worth carrying forward, or that insurance information 10 years down the road has less value or whatever. So those sort of types of decisions are made within the data lifecycle on how much effort you're going to put in to obtaining it, storing, sharing, maintaining it, and then when you're going to dispose it, when that effort gets more than the value that you derive from the data. Does that kind of make sense? So today you really do need to think about data separately from an information system. And there's these two guys, maybe they're guys, I have no idea, DeLone and McLean, that have an information system success model. It was first published, I think, in the late 80s, and it was revised in 2003. So basically this is sort of their theoretical model for what creates information system success. It came out of the information system community, not necessarily health informatics, although it has been tested in health informatics and shown to hold. But they basically say that there's inputs of information quality, the quality of the system itself, and then service quality they added in 2003, as in like support for the system and the users. And that those three things impact somebody's intention to use the system, and the intent to use, along with those other three things, impact user satisfaction of the system, and then those impact net benefits. Oops, that's me. And so they've basically shown that they tested anywhere there's a number up there, they have tested the relationship in the model, which is kind of cool. So like for those of you thinking about doctoral research projects, you want to look for a theoretical model or make one, and then your doctoral project is testing one of those lines, testing it for usually causality. You kind of need to go past correlation to causality. So I put these here because the model for information system success actually includes the data life cycle concepts in there and data quality, but also because it's a great example for those of you thinking for a doctoral degree of number one, finding a theoretical model that applies to what you want to do, and number two, as you start thinking about your doctoral research, thinking of ways to test that model. Makes sense? And I put the reference in there if anybody wants it. No, it's really more about fundamentals of how not to screw up your research project by failing to manage your data good. And the regulations these are regulations for data that are submitted to the Food and Drug Administration for marketing authorization decisions or other regulatory decision making. And basically the goal of this regulation is to assure that electronic signatures are as trustworthy as their paper signatures. And in order to do that, that requires software validation. It requires software security, so you can't put a fake signature in there, kind of, get in there and do it. It requires procedures for certification that an electronic signature equals a legal signature. And it requires procedures to ensure that people are qualified for their jobs. And then it also requires procedures for traceability, for tracking all changes to the data and tracking them in a way that a human can't interfere with it. And that's referred to as a system audit trail. But I put the FDA regulation in here. First of all, it's 3 pages. I highly recommend that you read it. The link's down there. Literally, it is only 3 pages. It is a great read. And it basically, it covers both the data aspects as well as the software aspects. And it really does a very good job at showing how data concepts and software concepts come together to assure reliable data for regulatory decision making. So I put that in there as an example. But really seriously, the goal being, if I say non-repudiation, does that make sense to everybody? Okay, so non-repudiation basically means that a user can't repudiate actions taken under his or her user ID in the system. So it means that all those things are in place: the validation, the security, the human resource procedures, the data tracking, the audit trail. All of those things are in place such that people can't deny actions taken under their name. So if we had a celebrity come here to UAMS for treatment, there's an audit trail on Epic. It tracks views of the data. So if that were to happen, people would look at that audit trail and make sure that people who don't have a need to know aren't looking at that patient's data. And so that's sort of what they mean by non-repudiation, because then they go back to the person and they say, dude, you looked, you weren't supposed to look, you violated the procedure. They can't say, it wasn't me, because their user ID is attached to that look, and that look is saved in the record. Yes, Alicia?
And that actually happened to me.
Did it really? Oh, they came back and they said, what were you looking at?
Yeah, and I said, no, look at me. And they were like, okay. So they were able to pull up. They had an envelope of times from the beginning of my shift all the way up to the time I logged out, and they had every computer I had access, every chart. So it was a particular person that was here, and what happens is in the morning time that we count treatments for the day shift supervisor. And so they had, the patient was deceased, but they didn't take it out. So even though I clicked on the chart, it still, it caught it, even though it was a second or 2 seconds.
Yep.
And so I was like, I was out of town when I got the email, and I was like, oh, somebody had to access my password or something. I left it up, but they figured out that I wasn't looking into the patient's chart because of the time.
Yep.
I get you.
Yeah, so that's really the goal of Part 11, is to make sure that we're responsible about understanding that our systems work as we've designed them to work, which is not always an easy thing. Okay, so that is it for today, guys. I did post you a quiz online, and it's for the rules, the workflow, and the knowledge acquisition and management stuff. So that's there. There will be a quiz for this week, and unless you guys, do you want me to do a quiz for this week, or do you just want me to put it in the practice exam?
Last week and a quiz for this week?
Yes. Do you rather not have a quiz for this week and me just to put it in the practice exam? Yes.
Yeah. Sure.
Okay. Then it'll probably be more on the 50 side of questions, but they'll be in there in the practice exam, which was probably safer for you guys anyway. The more questions is in there. So, okay, guys, thanks very much. Have a good afternoon.